Let's start with the first session that we have today. Is called Research on Agriculture 4.0. And our first keynote speaker is Dr. Manuel Silva from the ISEP, research institution from Porto. And he will give us its talk entitled The Contribution of Robotics to Agriculture 4.0. So Dr. Manuel Silva, thanks for joining us, and the floor is yours.
Thank you very much, Albert. Thank you for this invitation. It's a pleasure for me to be here to talk with you about these topics. Again, welcome everyone. Good morning to everyone. I would like to thank you for this invitation to be here. As you stated, I am a teacher at the School of Engineering of the Porto Polytechnic, so it's ISEP IPP. And I am also a senior researcher at INESC TEC. INESC TEC, it's a research lab here in the north of Portugal in Porto. I am affiliated with the Center for Robotics in Industry and Intelligent Systems. And although the name is Industrial Robots or Center for Industrial Robotics, in fact, we also have a group or a team working on agricultural robotics here at INESC. And well, in fact, I am not the leader of this team. The leader is my colleague, Filipe Santos, but I have been collaborating with them in some projects and in some areas of this research that they are doing. And so I will just make here a brief introduction to the contribution of robotics to agriculture 4.0. And so regarding my presentation, it's organized in this way. So I will start with a brief presentation of this topic. Then I will present some of the challenges that are faced by agriculture. And for some of these challenges, we believe that robotics might be a solution. And after that, I will just describe some of the possible applications of robotics in agriculture and also some of the difficulties that are being faced while trying to develop robots for this area. And after that, I will just present two projects on which we have been involved, mainly on the area of localization, path planning, and mapping for agricultural robotics, that it's still an open area of research. And finally, I will conclude with some remarks and some ideas for future developments that can be made in this area. So for starts, I think that it's well known, let's say, that agriculture, well, not just agriculture, the entire world is facing some challenges, and some of them are particularly relevant to agriculture. So what we are witnessed is that the forecasts predict that the population will grow by around 2 billion people in the next 30 years. And this will create a huge need to feed all this population. And we need to feed this population with quality food, which is not easy nowadays. Another problem that we are facing, and this is particularly relevant in the developed countries, and this is the image that I have here, it's for Europe, is that there is a huge population aging. So what we are seeing is that also in the next 20 to 30 years, it's believed that the average age of European people will increase by 4.5 to 5 years. And so we are seeing that we are having more old people than young people. And this will be also a huge problem, not just for agriculture, because there won't be enough people to work on this area. And we as Europe and also North America, we have some problems, let's say so, regarding the receiving immigrants. But also what we are witnessing is that immigrants are the ones that are working on some of these tasks, and they are being able to solve some of our problems. And so this is another problem that it's also increased by this third problem, that it's lack of human labor, in particular in agriculture. This is also some numbers for Europe, and what we are seeing on this...
3,2,5, 3...
Sorry. And what we are seeing in this image is that there is a lack of human labor in agriculture. So most of European farm managers are above 45 years, and this trend will increase in the next few years. So besides these problems, we also have the problems of climate changes. So we need to work on agriculture without destroying the ecosystems. And furthermore, and also regards with these problems, we also have the problems of the need for more sustainable cultivation practices. So one of the problems that we have is that we are spending huge amounts of herbicides and pesticides just pulverizing or spraying crops, in some cases just by prevention. And with this, we are increasing the dangerous products that reach the water levels. And so what we are witnessing from all of this is that we also have an increasing demanding and aware consumers. So consumers are being faced with all these problems, and they are asking for more sustainable and healthier products. And regarding this, one of the trends from consumers is that they want more vegetables and fewer animal products in their diets. So this is the situation that we have nowadays, and these are the main challenges that agriculture is facing. And regarding all these problems or this situation, we as mankind, we have tried to find some solutions, okay, but none of these solutions is in fact possible to solve all these problems. And for instance, some of the solutions have been, for instance, the use of vertical and agriculture and intensive agriculture. And here we have been able to create foods almost without needing land, which is from one point of view very interesting, but there are some consumers and many consumers that are looking for biological products. And so we are also faced with the situation of having to continue, let's say so, with the traditional agriculture. And besides that, in order to reduce, for instance, the meat consumption, we have tried to develop lab-grown meats, but there are also several consumers that don't appreciate or that have some resistance to this sort of solutions. And besides this, one other situation or one other alternative might be the use of insects for human consumption, which is also presenting several difficulties of being introduced in the market. And so this is the present situation. And what we see from this is that there are several challenges that are being faced by agriculture. And what we see, what we try to achieve, or what we want to achieve is to have some more sustainable agriculture, but we want to reach this sustainability without compromising productivity. So we want to have an agriculture or a traditional agriculture that it's competitive. And we can at least increase part of this or have agriculture more competitive by use some of the already available technology and also developing some new technology. And here I am, in fact, considering robotics. So the solution is to develop what we might call precision agriculture or agriculture 4.0. Okay, for me, these two concepts are very related, and I would say that they are almost the same from my viewpoint, okay? So for those who are not aware, when we speak about precision agriculture, and this is a definition that I like it very much, it's a management strategy that uses electronic information and other technologies to gather, process, and analyze spatial and temporal data. So we need to collect lots of data, and with that data, we are going to analyze it. So the purpose is guiding target actions that improve efficiency, productivity, and sustainability of agriculture operations. I usually say that agriculture 4.0, it's like the Facebook or Instagram of machines. So we have lots of sensors. We can see it like people that are publishing information on the social networks. So we have lots of sensors collecting lots of information. Okay, so we have, for instance, cameras, but this is the most traditional, but we can also have different kinds of sensors. All this information is collected. For instance, this is an example of an orchard. This information can be collected in different points of the orchard and can also be collected a long time. And then this information is fed to a computer application. It can be, for instance, in the clouds. And here we have some computer algorithms. We are mainly using artificial intelligence algorithms, and we are treating this information. And with all this information, we can, for instance, determine if there is a specific spot on the orchard that needs to be fertilized, that it needs to be sprayed with some herbicides. And so we can do what we call the precision agriculture. We only actuate where it is in fact needed. And for this actuation, so if we already have all this digital information, we are not going to feed, or we don't need to feed this information to people, but instead we feed it to machines, okay? To machines, to robots. So we can also have, for instance, a swarm of robots that receive orders, and we can have, for instance, wheeled robots or tracked robots on the ground, but we can also have, for instance, drones on the air. And all these robots receive orders and they organize themselves to solve the problems of agriculture, okay? So sorry, I'm a bit cold. Sorry for this. And so what we have, or what we see, is that agriculture 4.0 is the union or the reunion of these three main areas. So we have IoT, so Internet of Things. So here we have lots of sensors, lots of information being collected, okay? All this information that we receive with all those sensors is then fed to some, I would say, mainly artificial intelligence algorithms. So we try to develop algorithms that behave in some sort similarly to the way humans think, okay? And with all this information, and after thinking or analyzing this information, then we can take some actions, and these actions are performed by robots, okay? And so this is where robots are used in the scope of this agriculture 4.0. And so I would now go to the next section, and I will just present some of the applications of robotics in agriculture and also some of the problems that are being faced in this area. So when we consider all the tasks that are needed in agriculture, we see that presently we already have several solutions, or I wouldn't say commercial solutions, but at least we have several research groups working on researching solutions for all these situations. So we have robots being developed, for instance, for land preparation before planting. This can be, for instance, for plowing and also for fertilizing, okay? And here in fertilizing, we can have fertilization on the ground or using drones. We have both solutions. We also have robots being developed, for instance, for sowing and for planting crops. Then we have lots of developments on monitoring the health of the crops. And when I mean monitoring the health, I also mean for plant treatment and for pest control. So robots that are just analyzing how the plants are developing, if some pest is arising, and try to solve that problem. And then we have also several robots being developed for harvesting applications, because harvesting applications are some applications that involve a huge amount of human labor, and that account for a huge percentage of the costs of the agricultural tasks. And finally, we also have in, I would say, a less scale, some robots for yield estimation and for phenotyping of plants. So regarding all these applications in agriculture, what we see is that robots, they are required to at least comply with 4 peak areas, okay? So we need first to choose an adequate platform for the mobility of the robot and also for steering. So we need, let's say, the mechanical part of the robots, not just mechanical, because there also needs to be the electronic control of the motion, but this is mainly concerned with the mechanical part of the robots. Then, if we want a robot that performs something useful, the robot needs to go from one point to the other. For instance, he needs to move between the crops without damaging those crops, and knowing where it is so that it can, for instance, apply some fertilizer or some herbicide in some specific spot. And this is what we call localization and navigation. So he needs to know where it is, localization, and he needs to go to the spot that we want. This is navigation. And then robots also need to be able to sense the environment, sense the crops, sense the plants, and also to detect the targets on which they want to perform something useful. And finally, depending on the type of crop or depending on the type of fruit that we are considering, the robot needs to have an appropriate end effector. So the end effector can be a spray tool for spraying herbicides or fertilizers, but it can also be, for instance, some sort of cutter for pruning or some gripper for picking berries or for picking apples or oranges or stuff like that. So regarding each one of these topics, when we are speaking, for instance, about the questions of mobility and steering, what we see is that the majority of robots that have been developed for agricultural tasks use wheels. They are mainly four-wheel drive robots, okay? So four-wheel drive robots, they are very adequate for these sorts of environments because the terrains on which the robots have to move are typically irregular and they present better characteristics than two-wheel drive robots. Anyway, four-wheel drive robots don't solve all the problems. They are very used because, in fact, it's a technology that it's very well dominated. But one of the solutions to overcome some of the problems is to use tracked robots. However, tracked robots have the difficulty or the problem that they destroy the soil. So when they go several times over the same spot, they compress the soil, and this damages some of the soil qualities. So an alternative is to use legged robots. Sorry, this is still tracked robots. So one alternative is to use legged robots. And what we are witnessing is that there is being a huge investment in legged robots, and we are now witnessing the first legged robots being developed for agricultural tasks. Legged robots have the possibility of walking on very difficult grounds with, for instance, steep slopes, with rocks, with ditches, and they can place the feet on disparate places on the ground. So they can, for instance, avoid obstacles and holes on the ground, and they don't damage the crop. So they can, for instance, place the feet on places where we don't have plants. And another alternative is, for instance, to use unmanned aerial vehicles, mainly for spraying and also, for instance, for detection of yield estimation and detection of health problems in plants. And finally, mainly in structured environments, for instance, in vertical farm, what we see is the use of rail tracks for having robots on top of those rail tracks that are able to run along the entire crop. So the other situation is localization and navigation. So this concerns the movement of the robot through the crop fields. And as I stated, what we want is the robot to go from one place to another one without damaging the crops and also avoiding obstacles. And this is a very, very challenging task for autonomous robots. So in fact, in closed environments, for instance, in factories and even inside houses, we are already being able to develop robots that are or that present very good localization characteristics. They are able, for instance, to follow what we call natural contours. So they make a map of the environment, and based on that map of the environment, they are able to go from one place to the other. But typically, that is not the situation on crop fields. While in factories and in houses, those natural marks are typically static, so they don't change along time. That does not happen in crop fields. So plants grow. We have, for instance, branches that fall in the ground. Some of the plants die, and so these natural marks, they just disappear. And another problem is that while in factories and inside home, we have some environment conditions that are more or less static, so we can control, for instance, the illumination. We don't have, for instance, fog, we don't have dust. When we are outside, all these factors, they just degrade the performance of sensors. And so it's relatively difficult, or it is still relatively difficult, and it presents several challenges to develop robots that can perform navigation very well in outdoor environments. So we have been using, researchers have been using several different navigation technologies. mainly based in global navigation satellite systems. So this is what we usually call GPS, but it's not just GPS. There are other systems for this. But GPS has a problem. If we cannot spot the signals from the satellites, so if they are not in our line of sight, we lose the signal. And this is sometimes a problem when we are working, for instance, in orchards on which we have trees that are just hiding the signal. And so for this, we need to join these technologies with some other technologies, like for instance, the use of inertial measurement units that just measure the accelerations, the linear and rotational accelerations. And by double integration, they allow us to see how our position or the position of the robot is evolving. And another possibility here, it's also to use visual odometry. So to use information from cameras, from artificial vision, to understand how we are evolving on the crops or on the fields. Another situation that we have, and it's a very important one, it's the question of sensing and target detection. So this is one of the most relevant applications in agricultural tasks. And this is, let's say, the core problem, because if we want to do something useful, we need to identify where we want to perform that work. So we need, for instance, to detect if the plant is with some health problem. We need to detect where we want to pulverize or to spray a plant. We need to detect where we want to cut a branch if we are pruning, and we want to detect, for instance, where we can find a fruit if we want to pick it up. And this also brings lots of problems to researchers, because, for instance, plants, they are not all equal. Okay, so they grow with different orientations, different characteristics, different colors. When we are in the field, we have different sun orientations, so we can have the sun from the front, from the side, and all these makes very difficult to clearly identify all these situations. And for this, what we have been using, it's mainly computer vision systems with several different sensors, and we still have not found any particular sensor or any particular algorithm that can solve all of the problems that we have been facing. And so this is also a continuous research line. And also considering here the sensing and the target detection, we have to consider that when we are trying to detect the targets, we also have different needs and different phases. So first, we need, for instance, to detect vegetation, okay? And for instance, if we are picking up some fruit, we need to detect where are the leaves of the plant, for instance, and these leaves can be occluding the branch that we want to cut. So we need to detect from one side vegetation, and then we can need to detect, for instance, some pest or also some branch to cut or some fruit. So besides all of the problems that I have already spoken before, we also have the need in the same robot or in the same equipment to detect different things. And so this also is more challenging than the applications that we have, for instance, in industrial environments. And finally, regarding the targets, so these targets or the detection of these targets can be very distinct depending on the tasks. So if we are interested in land preparation or sowing and planting, in these cases, we are mainly interested in detecting the area on which we want to perform our tasks. So we don't need very specific artificial vision systems or vision algorithms. But for instance, if we want to prune, we need to scan and measure, for instance, the structure of the plants, the branches, to know the exact place where we should cut the plants. And as I told you, there are no two plants that are equal. If we want to perform weeding applications, we need to detect the plants and we need to differentiate between the crop that we want to grow and what is a weed and we want to eliminate. Okay? If we are concerned or preoccupied with, for instance, spraying applications, we need to be concerned, for instance, that leaves, they change color, they change shape with their growth. And so there are already here several problems besides the problems that are concerned with the plant health. And sometimes it's very difficult, for instance, to detect plagues on plants because, for instance, the insects are on the opposite side of the leaf. And so more problems that are being presented here. And finally, when we are considering harvesting or fruit picking, some of difficulties is that here the robot must go from plant to plant, must detect the fruit that it wants to pick, and it needs to pick it up without damaging the fruits. And so this is also some very difficult problem. And based on this, I'm just going to present now two projects. I had here some more information, but I don't have the time. It's two very brief projects from INESC TEC, okay? So at INESC TEC, we also have a team that is working on research for agriculture. So we are mainly focusing on the development of robots and automated solutions for these tasks. And our roadmap, it's mainly this. So we are starting, or we have started by the monitoring applications that are, let's say, the easiest ones to solve, although there are already several challenges. And then we are going up on the scale and we are going to spraying, pruning, and harvesting. And what I'm going to present, I will just skip these two slides. I will just start by presenting this video with some robots that we have developed. And while the video is being shown, I will just describe the robots, okay? So here I'm going to present the Agrop version XX robots. So I will talk about version 14 and version 16. And these were two of the robots that we have developed. And they are mainly for applications in the vineyards of the Douro region. So this is the Agrop version 14 robot. So this was a robot that was developed to monitor the vineyards of the Douro region in Portugal. And those vineyards, they are in steep slope terrain. And this one is the Agrop version 16. It's a development of the previous robot. So it's a bigger one. And it's developed for yield estimation and pruning tasks. And we have mainly worked on the improve the robot localization and positioning. And what we are seeing here, it's the use of artificial vision systems to detect the plants and based on that to be able to localize the robots. So this is the version 16 robot and we can see it now working on some vineyards, and it's being able to follow those steep terrains. So for this robot and to improve the robot's localization and positioning, we used a wireless sensor network, and we integrated the concepts of IoT and SLAM. So this robot, it reads what we call the receipt signal strength indication. So there is a Bluetooth low energy network, And this network, it just sends some signals, and based on the intensity of the signal that it's received from this network, the robot is being able to understand where it is. Anyway, you can see that, as I told you, so four-wheel drive robots are what it's more common today in agriculture, but you can see that while it's moving, mainly in very steep slopes, it still presents some difficulties. I believe that the time is going on, yes, so I will just skip the next slides, and I will just go to the conclusions. So from what we have seen and from what we have been analyzing, what we see is that there is a huge research interest in these sort of applications. But what we have seen is that there is still a very small number of commercial products. So mainly, we are mainly in the research area yet. And the main limitations that we find here in the robots that have already been developed is that they present a relatively low speed when compared with human operators or with human labor. And the success rate, it's also relatively low. Okay, so we are speaking about success rates around 80 to 90%. And this is very difficult due to those variable ambient conditions that I've stated before. And regarding the major areas that we are predicting that need future research, I believe that we still need to develop lots of technologies concerning locomotion systems, sensors or different types of sensors for detecting the plants and the pests and stuff like that. And we also need lots of work on the computational aspects of these technologies. So we need to develop more robust computer vision algorithms and also artificial intelligence algorithms for identifying these situations. And so with this, I conclude my presentation. And if you have any questions, just please feel free to ask it now, or if you want, you can even email me. You have down there my email. Thank you very much. And it's all.
Thank you very much, Dr. Silva. In here, there's a question in the chat.
Yes. So in summary, which robotic solutions we already have in the market? So we already have, for instance, robots for plowing, and we also have robots for weed control. And regarding weed control, we have, for instance, some small robots that are being developed by, I believe it's a Danish company. The robot is called TERRATECH, and I believe it's the first home-use robot. So we can already use the robots for weeding if we have, for instance, a small garden or a small place where we grow some foods. And right now that we are starting to see some companies, for instance, DJI, it's a very important company that develops drones, and they are developing commercial drones for yield estimation and also for identifying the health of crops.
Thank you. There's another question.
Yes.
From Harshi.
I'm curious to know what characteristics the robots monitoring crops in phenotyping application of robotics. Well, from my knowledge, they typically detect the height of the plant, I don't say the quality of the plant, but they try to see if the plant grows well or not, and then the yield of the plants. If you see on the bibliographic reference that I have here, there is a chapter that it's a state-of-the-art paper, and there is a chapter that it's devoted to robots for phenotyping application. We don't have, or at least there are not many examples, but you can see there 2 or 3 examples of robots for phenotyping applications. And do you have an idea of the comparison between the time spent by a person and by a robot like those we saw to perform the same task? Well, it depends. If we are, for instance, discussing about, for instance, spraying, spraying or pruning, humans are much, much faster than robots, okay? We are much faster because we are faster identifying the plague. So we look, let's say, at the plant and we immediately process the information and we detect if it's a plague or not, and we can just spray it. If we have a robot has to interpret that, so it has to run some specific algorithms, and sometimes it fails. If we are discussing pruning, humans are much, much faster than robots. It's the difference is still bigger. But for instance, if we are discussing about picking applications or picking, I would say mainly strawberries and tomatoes, what we are seeing is that there are already some robots that present different or several arms, and so they can make the task in parallel. And in these cases, the difference is not so big for humans. So the same robot can replace several humans. There is a robot, I don't remember the name, that can pick strawberries, and in 24 hours it makes more than 1 acre for picking strawberries.
Okay, thank you. I think that there's no more questions from the audience.
Thank you very much.
So again, Dr. Silva, thank you very much for joining us in our workshop, where this was a really nice presentation. And thank you again.
Thank you, Albert. Bye-bye.
Bye.